Can you see the slide changing?
Can you see your slides?
Okay. So is it changing correct? Like different pages?
No.
Oh, is it just staying?
Still the first page.
Oh, okay.
I can see your mouse is moving, but it's still the same page.
Oh, okay. Maybe.
Well, it is changing right now.
Oh, okay.
Going to the next page.
Thank you.
Sure. Okay, I think time is up, and maybe we can start. So hello everyone. Today we will discuss a paper on Graphomer, which is a version of a graph version of the transformer. And Xiaoying Liu today will help us lead the discussion for this paper. And we can give the time to Xiaoying, and Xiaoying, you can start when you're ready.
Okay, hi everyone, I'm Xiaoying Lu, and I'm going to present this paper, Do Transformers Really Perform Bad for Graph Representation? It is a paper from Microsoft Asia, and it is also a proceeding of NeuroReps 2021. So here's the outline, the sections I will be covering today. And the reference part is for materials I used for this for slides and not for the not the complete reference for this paper. So first of all, the introduction of this paper, and I will also cover some of the background. First, this paper is just mainly be doing graph representation learning. So what is graph representation learning and what is a normal GNN looks like? So first of all, we need to input a graph. But what exactly is like to input a graph into GNN or a transformer like this paper did? So first of all, we the input layer, like here, the index 0 means layer 0, which will be the first layer and the input layer. So for first layer, the input is the node feature of the or of each node. So this I index means the ith node. And then inside GNN, each layer represents a hop distance inside a graph, or to say network. These are just some interchangeable terms. And yeah, so for each layer, they aggregate the node feature of one particular node. In this case, will be the ith node. So they aggregate the feature information from the L-1 layer, and the aggregated function can be just simply the average of the feature or the summation or the or just pick the maximum value. So after aggregate all the information from last layer, and then the combine function will be combine this AIL at layer L, which is what we calculated here, the output of the aggregate function. And then this is the node representation from the last layer as well. So you can see the index is L-1, and then combine this old node representation and the aggregated neighbor features and combine them together as the new node representation for layer L. And finally, after all these layers, and you will have like all these learned new node representations. But our objective is actually to learn a graph representation. So how exactly I'll be just get that graph representation out of all these node representation. So here we have a readout function. So the readout function is to kind of also aggregate all the feature learned for each node. And then at the last layer, they aggregated all these features into just one representation. So the readout function can also just simply be a average or maximum value, or the more sophisticated to do a graph level pooling, but which will still somehow be the same. It's just pick the maximum value or the average value. And then after the readout function, we will get the graph representation. Okay, so this is the workflow of graph representation for, traditional GNN. So what are the features in graph? So as you can recall, we said that the input level is the node feature. So what exactly these node features are? So for example, if you have a social network and nodes representing people, and the node attribute can be the age of that person, or the gender of that person, or the score of their social activeness, and etc. So these attributes, sometimes we use the attribute as the more semantic, as the feature of with more semantic meaning, and the feature will be representing the ones that being processed in certain level. And the other example is node feature or attribute. So also if you have a social network, and the edge can be the connection between people on social media. So here the edge attribute will be one person like the other one's post, or one person commented under another person's post. So these can be the edge attributes. So even though we have a graph level representation learning, so but all these, as you can see, that the graph level, the graph representation is actually aggregated from all the new learned node representation. So actually there can be like 3 general tasks under all these, under the same workflow. So first one is node level prediction. For example, if you have a citation network, and the node will be a paper, and the node, here we should call it node feature because it is being processed. So the node feature can be the word-to-vec embedding of a paper's abstract and title. And based on the word-to-vec embedding of a paper's abstract and title, the prediction goal is what this paper is from, the field of that paper. So it can be like under computer science, and it could be like social science. So just based on the paper's abstract and title, how the representation is telling you that which field it belongs to. And the other one, the other task is edge level prediction. Still, if you have a citation network, the edge could be one paper cites another. And here the prediction goal can be the missing citations. So what exactly is this means is that for one example, they probably will just drop like 2 references, like real references. They just intentionally drop them. And then they will randomly sample 100 negative references and ask the model to rank from high to low, like which 2 are the actual real references that they just dropped. So this is a case of edge level prediction. So the third one is graph level prediction. And this one is what this work is about. And the example here is, I think it's just like what this work is mainly be used on, and which are that when you have a molecular network where the nodes are atoms and the edges are the bonds between the two atoms. And the prediction goal will be whether a molecule inhibits HIV virus replication or not. This is just an example, but basically it's just based on the whole graph. Yeah, if it inhibits that trait or not. Okay, so these are the 3 tasks. And this case is actually borrowed from the Open Graph benchmark, and which I will be talking about in the following slides. But by now, do you have any questions? If not, I'll just go on. So these are the data set that used in this work. First one is benchmarking graph neural networks. So in this benchmark, they provided many like real world graphs and also mathematical graphs, but here I didn't list all of them out because they only use, for this work, they only use the zinc graph. So zinc graph is also a graph that each graph represents a molecule. And the task of zinc is to make graph regression, which is labeled by four of the human metabolites prediction. Sorry, I don't exactly know what that is because I'm not a chemistry expert or I suck at chemistry. So basically, I just don't know what that means, but it's doing a graph regression task. That part I understand. So and also what worth mentioning is if you find zinc is like pretty much the data set you want, it has all kinds of variations, like different size. So the largest one is zinc full. Zinc full has like 249K graphs. So even though that each, because I think this is kind of an inherent problem is that graph representing a molecule. So the node will always not be that much, but the graph, the amount of the graphs are a lot. So if you don't think this one is enough for your work, you can find the other like variants like zinc full, or there's all kinds of different sizes. And the second data set is Open Graph Benchmark, and shortened as OGB. And here you can see that they actually provided many data sets for different tasks, and for different field, because many of the graph level prediction tasks are all just molecule graphs and to predict some of the features of that graph. But here you can actually see this code too. It's actually in the computer science field. It's not just to predict a molecule's feature or something. So I think this is one of the one of the trait of this OGB benchmark, that it provides data sets from all kinds of fields. As you can see that the node count is like nearly 5 times to the molecular data sets. But anyways, these two are the ones that this work use. So yep, and the third data set is Open Graph Benchmark Large Scale Challenge. Yeah, by its name, it's very intuitive. It's just 3 very large data sets, graph data sets. And these 3 are, belongs to 3 different task categories. And just like we mentioned, node level, link level, and graph level. So very intuitively, this work, GraphWarmer, is using this graph level large scale data set as the pre-trained model, and also just as is, and to evaluate its performance. Okay, so any questions by now? okay? If not, I will start to like introduce the graph former methodologies. So first of all, by the name graph former, and as Professor just introduced, it is just a transformer being used for graph data set. And just as the title, our graph formers really performs like bad on graph data set. And yeah, so apparently the answer is no. They achieve better performance than popular GNN architectures and also former attempts of graph transformers. So the motivation here is to answer the question that whether transformer architectures is suitable to model graphs and how to make it work in graph representation learning. So here's some comparison to the popular traditional GNNs and former graph transformer attempts. So before, some of the work just replacing the key modules, like what we just said, the neighbor aggregation functions in classic GNN variants by using the transformer softmax attention. So it's not directly being built on the transformer because it's just like replacing one of the modules. And second, some of the work only calculates the semantic similarity between nodes without considering the whole graph structural information. So that would be kind of bad, because if you only consider the semantic similarity between nodes, which means that you only considered, the worst case is that you only consider the node feature, that means you don't even consider the edge feature and how strong these bonds are, or yeah, the whole structure is being left out in this case. So what graph formers do, like how they improved in these 2 points, is that it is being built directly upon the standard transformer encoder, and also they add some structural encodings into the model to even improve the model's performance. So first of all, let's explain what is the structural encodings. So the first one they use is called centrality encodings. Centrality encoding. So what is centrality? Centrality is a measurement of how important a node is in a graph. So here I give you some example. It could be degree, it could be eigenvector, it could be betweenness. So imagine you have a social network. Yeah, as the example before. So you have a social network, and this network represents how active you are. The link is representing how you interact with other users on social media, and each node represents a person. So the degree, you can interpret it as how this node are socially active, because that means how frequent they interact with other people. And for eigenvector, it is the measurement of how influential this node is inside of this network. So what does it mean to like influential? What is it different from the degree centrality? So eigenvector is actually if this node is connected to other more popular nodes, that means that the eigenvector will be probably higher, because those nodes it connected to are also popular, or are also maybe with high eigenvector, or say higher degree. But if you are connected like to the nodes that is less popular, probably the degree of that node will be also high, but the eigenvector will be not as high to the ones that connected to also more popular nodes. And the betweenness is the shortest path count of it's the shortest path. Like if one node has to walk from itself to another node, how many times they have to pass you. So the betweenness can somehow be interpreted as how diverse and uniqueness your social activity is. Like if you know some people that is not with much friend, that means the shortest path from every node to that node will have to like pass you. So that means that you have a more unique social activity compared to others. So the interpretation part of the centrality of the centrality attributes is actually vary from a graph to another, because it depends on what is the semantic meaning of each of the node and edges. So anyways, for this paper, they chose to use degree centrality. And how they do that is to add a learnable vector to the node feature itself in the input layer. So here we just quickly review what the degree of a node is. So it could be like for directed graphs, it could be in degree and out degree. So for example, if you see node 6, the in degree will be 1, 2, 3, 4, 5, 6, and the out degree will be 1 and 2 and 3, right? Yeah, that's probably it. So that's what directed graphs are counting the degrees. But what if it is like undirected? For example, if all these are without arrow, for also node 6, it will be 1, 2, 3, 4, 5, 6, 7, 8. So total degree will be 8. Okay, and this is just the equation of how they actually do that. And then this z minus and z plus is just the learnable vector you mentioned here. So the learnable vector that is indexed with the out degree. Yeah, and also the index with the in degree. So I actually forgot which one is, but anyways, one is in, one is out. I'll go double check later. So anyways, so one is in and one is out, and but they are just the index. They are just the indexes of that learnable vector. And as you recall, this xi is the original feature of the ith node, and these three like summation, the summation of these three will be the actual input of the ith node. So these three forms a new feature of node I. And yeah, because I was kind of confused at first of that index thing. So here I give you a small example what the index thing actually means. So for example, if you have, if your like z minus is like this array, and the index is like 1 to 10, which will representing the in degree of the in degree of a node. So if your learned value is from 10 to 100, that means that the network is learned to pay less attention if you have less neighbor, and pay more attention if you have more neighbor. Yeah, that's how this is working. And the second structural encoding is spatial encoding. Here they want to answer that how to exactly add positional embeddings like transformer does, because we know that transformer actually add positional embeddings, right? And but for graph data, how do we actually do that? So we need a connectivity between the nodes in the graph. So it may not be very intuitive, but you can see that if you only have a data set that's with a bunch of nodes and bunch of edges, so how exactly are you going to present it in 3D world, or even say like 2D world? How do you draw a graph like this? So you may probably need something to indicate the distance. For example, why is it like placed like this instead of this node to be here? So there must be some certain measurement of that. And here, this work use the distance of the shortest path, and let's just call it SPD. in the following slides. So how are they doing that is to add a learnable scalar, which will serve as a bias term in the self-attention module. Here, the self-attention module is the attention module inside the transformer encoder. And what exactly the SPD value will be for a pair of nodes. So if the two nodes are connected, SPD equals to the hop distance in between. So for example, from this node to this one, so probably the shortest path is 1 and 2, right? So it's 2. And if the two nodes are not connected, SPD equals to a special value. Here they use -1. And let's say that this 2 has no any path that can like ever walk from this node to this one. So these two are not connected. And so the SPD will be assigned to -1. And you can see that this is the attention value, right? So this part is basically just how transformer calculated the attention value. But here we add one more bias term. So this bias term is just calculated as what I just described. It's just using the SPD. The SPD is just the index of this learnable vector. So what inside B is all learned, but the index of B is assigned by the SPD. Yeah, so just like the degree encoding. So the last encoding is edge encoding. So here they want to answer the question that how to better incorporate the edge feature information by exploiting the global information transformer architecture provided. And yeah, so here, because there are many attempts to incorporate the edge feature. So here they just wanted to like further improve the performance of incorporating the edge feature to make it more expressive. Yeah, so they try to learn a edge embedding along the shortest path for of each node pair. So yeah, what exactly does that mean is that from walking from node I to J, the shortest path can be many edge combination, right? So from edge 1 to edge N is the shortest path from node I to J. And for each edge, and each edge has its corresponding edge feature. So that's XEN. And XEN will be multiplied with this learnable vector, which we call it a edge embedding. So these two multiply together, and then to take the average of every edge plus the edging, every edge here, every edge feature plus, multiply with the edge embedding and take the average of it and serve as one of the other bias term in the attention value. So it's just like added here. Okay, so any questions here? If not, let's just review the three structural encoding and what the contributions are. So for centrality encoding, other than just have the semantic correlation between nodes, they can, with this centrality encoding, the model can also incorporate the measure how important a node is in the graph. And with spatial encoding, it allows each node to attend to the information to any position at a learned level. By saying at a learned level is that just like because it is the index that is the special, the shortest path hop distance. So how much focus on what hop is being learned by the bias term. And also the same with this one, the edge encoding. And yeah, it allows the model to leverage information from all possible related edges of the whole graph compared to previous attempts previous attempts are all incorporate only the edges that is directly associated to the node. So how exactly we're using all these encodings inside the transformer encoder? So this one is just describing the attention module in the transformer transformer encoder. So if you remembered, the node feature will be added with the centrality encoding, which is degree centrality. So adding it and thus use the summation as Q and K and V. And yeah, this is just what inside the transformer. And yeah, here after before softmax, the attention value will actually be added with spatial encoding, which is the hop distance of the shortest path. And this one is the edge encoding, which they are taking a dot product of a learnable edge embedding vector with the edge features. And they are like doing the layer normalization before the multi-head attention and the feed-forward neural network, feed-forward network. And this is proved in one of the work that it helps stabilize the optimization. And one of the methodology inside this work is that they added a special node to perform the readout function. As you recall, the readout function is to aggregate all the learned node representation and to combine it into a graph representation. So instead of doing that, Graphformer use a special node called vNode. And then they will make connection between vNode and all the other nodes individually and treat vNode just like a normal node while training, but it collects all the information over the whole graph along the training process because it is connected to all the other nodes. And also because vNode is actually an imaginary node. Instead, we don't want other nodes to put too much focus on it because it is, we wanted it to aggregate all the information, but we don't want wrong attention on it. So non-physical edges, which means like from vNode to VJ or from VI to vNode. This work resets all the spatial encodings, and this is what I guess, the edge embedding as well for corresponding non-physical indexes to a distinct learnable scalar, like to make difference to, what I guess is like they set it to 0 because they don't want it to, like it to put more focus on it. Okay, so any questions here? Okay, so after we will start to analyze why Graphformer is like better than traditional GNN and why is that? So first of all, like why is Graphformer, like how powerful is Graphformer? So fact one is that the distance of the shortest path can be used to improve Weiss-Feiler-Lemon test. So what does this WL test do? Is that to test if two graphs are isomorphic. So what does it mean? Like two graphs are isomorphic. So there are like three things they have to meet to be isomorphic. So first of all, there has to be equal number of vertices and equal number of edges and same degree sequence. So what is degree sequence? So for example, for these two graphs, the degree sequence is because this one has degree 2, right? And this one has degree 2, this one has degree 3, this one has degree 3. So like from left to right is like all red and blue. So this graph degree sequence is 2, 2, 2, 3, 3. So this 3 is like coming from the blue node. So the right graph is also like 2, 2, 2, 2, and 3, 3. So which we call like it is failed to distinguish these two graphs, even though they're actually different. But for WL test, they cannot distinguish these two graphs. But if we use SPD sequence for this graph and the red node, and well, let's say that for SPD, they are calculating like from this node to this one is the shortest path is 1. To this one, the shortest path is 1. To itself is 0. To this one, the shortest path is 2. And to this one is 2. And to this one is 3. So the same case goes to all the red node. And for the blue node, the shortest path to itself is 0. To this one is 1. To this one is 1. To this one is 1 as well. To this one is 2. To this one is 2. So based on the what I just described, we can have these SPD sequences. So for the left graph, and for red node, the sequence looks like this. For right graph, the red node, and the sequence like this. You can already see the difference, right? And for blue nodes, the left one looks like this, and the right one looks like this. Even though for blue node, it cannot distinguish that, but for red node, it can be distinguished. So, and inside this paper, graph isomorphism network, and they prove that message passing is equivalent to the WL algorithm. So here we can say that graph former has a more expressive message passing way than at least for GIN, because they're using WL algorithms. Okay. And fact 2 is that by choosing proper weight and distance function, the graph former layer can represent aggregate and combine steps of popular GNN models. So the first one is that if they wanted to use mean aggregation and also the same setting for combined function, they can just set this bias term to 0, and yeah, if the distance is 1, because they're only considering the first hop neighbor instead of like 2 hops more. And yeah, so they're only considering this one, and the other one is just negative infinity, so that after the softmax, they can approximate the hard softmax. And also because we're not doing attention anymore, so the query and the key will be set to 0, and the value will be set to identity matrix. For some aggregation, it is under the premises that you have the mean aggregation implementation already. So it will be mean times degree. So where is the degree coming from? Is that, if you remember, the centrality encoding we're using is the degree centrality. So this information is already known inside the model. So if you have mean aggregation and you wanted to like approximate the sum aggregation, you can just simply times it with the degree value. What if you wanted to approximate the max aggregation? So first of all, you have to use one more attention head to find the maximum, to find the max value over the T neighbors. So also similar settings here, because we're only considering the directly connected neighbors. So if the hop distance is more than 1, we'll just set it to negative infinity to approximate the hard max instead of soft max. Yeah, we're still doing soft max, but because it is being set to negative infinity though. And this value and key will be set to the standard basis of the teeth standard basis, so that only the teeth value will be preserved while you time with this matrix. And the query will be set to 0, and the bias term will be set to T1. So T is just the temperature scalar, and the 1 is a all one vector. So the temperature must be set large enough to also push softmax approximating hardmax. It's just like the settings above. So fact 3 is that by choosing proper weight, every node representation of the output of the graphormer layer without additional encodings can represent main readout functions. So yeah, it's pretty much similar to the previous slides. If we set like, because we are not doing the attention right now, so the query and key are set to be 0, and the bias term to be will be set to temperature 1. And also the value will be set to identity matrix. So also you still need to choose a large enough T to like, so after, because these two bias terms are all temperature times with all one vector, right? So after these two times together, it will be like T1's to the power of 2. And if you have to choose large enough T for this term to dominate the spatial encoding term. So that's how they prove how powerful the graphormer is. Okay, so, well, any questions here? If not, I will just go on to the experiment part. So first of all, for this experiment, they use two kinds of graphormer setting. So one is with 12 layers, and the feature, the hidden layer, is 768 dimensional features, and they have a smaller model, which has 6 layers and 512 dimensional hidden layers. So 512 dimensional features. Yeah, and all the models are trained on 8 NVIDIA V100 GPUs. So I'm not sure what kind they're using, but each of the V100 can be 16 gigabytes memory or 32 gigabytes memory, and they are trained for 2 days. So here you can see how big the model is. And this is the result on this PCQ M4M LSC. So LSC is from that large scale challenge data set. Okay, so they are using MAE, which is mean absolute error, as the matrix here, and the mean MAE equation is as follows. So just take the absolute value between of the difference. Okay, so yeah, this is their result. They're comparing with GCN, GIN, and the version of them with V nodes. So the same setting as what graphormer have. So probably, yeah, so this is just variants of the traditional GNNs. And also the GT and GT wide is the former attempt of graph transformers. So GT wide is like, well, directly wanted to make it a fair comparison, because the hidden size is much smaller than graphormer. So they increase their the feature size of the graph transformer to also 768. But as we can see, the parameter increase a lot, but the result is not like actually reflecting the parameter increase. But for Graphformer, from small to large, it actually has a large like performance hop. And this is how they address the conclusion that Graphformer architecture is not exhibit the over smoothing problem, because the performance is actually still getting better while the layer increase and the parameter increase. And for the other experiment, they are measuring the transferable capability of a Graphformer model pre-trained on that data set we just saw. And because this Graphformer is a very large model, and so the data set they're using is relatively small for them, for the parameter counts they have. So they use data augmentation for graphs, which is from the paper called FLAG. So FLAG is just using an adversarial adversarial perturbation. Sorry, I just forgot that word. Okay, so it is using the adversarial perturbation on node features. So they directly add that perturbation on the node features and to do the data augmentation for graphs. So it is a modification on the node feature itself. And the result on OGBG. So OGBG means Open Graph Benchmark on graph level prediction data sets. As you recall, they are using these two data sets. So this one use AP as the matrix, and for this one they use AUC. AUC is just the area under this curve. So this is the plot of true positive rate to false positive rate. And for AP, it's just the precision, average precision, and this true positive divided by true positive plus false positive. So they also like compare with the traditional GNN, and also the traditional GNN fine-tuned with the same data set. And this one is also fine-tuned with the same data set. But the Graphformer is all using the extra data using this data augmentation methods. So for the last experiment, they're using, because for this one, they don't actually, encourage people to do pre-training. So they did not use the pre-trained checkpoint. So here they train a new model called Graphformer Slim from scratch on the Zinc data set. So the setting is like they are having 12 layers and the feature dimension is 80 and the total parameter is 489K. And the result on the benchmarking GNN data sets, which is Zinc. Yeah, so it's as follows. And GT and SIN is actually the former attempt of graph transformer, but as you can see, they don't perform better than the traditional GNNs. So, and so that is why, I guess that is why they said their title is Do Transformers Really Perform Bad on Graph Data? So that is because former attempts did not exceed, did not like being comparable to the traditional GNNs. And this is the ablation test. And they are trained on this large scale data set, also with 12 layers, and are trained for 100K iterations. So for the test, for the first test, they are trained with 1 million steps. And also they added one of their experiment is to use Ablation positional encoding instead of their own spatial encodings. The choose of this positional encoding is because in one of the literature, it shows that it outperforms other kind of positional encoding used in GNN literature. So as you can see with this one and this one, the error is actually decreased. So which means the spatial encoding in Graphformer is actually outperforms, but outperformed this one using Ablation positional encoding. And and they just keep adding their structural encodings inside. So for centrality, it also has a error hop, and also for edge encoding, they tried 3 different kinds. One is via node, one is via aggregation, one is via attention bias. So this one is what they proposed, but they also use like 2 different kind, two different places to add the edge encoding to see if this one is actually the best. So as you can see, via node and via aggregation is actually not much difference, but if it is added as the bias of the attention, it actually has also a error hop. Okay, so is there any questions by now? If not, I will start to start the related works section. So for graph transformer, for previous attempt, there are like some of the variations. So one is that they use one additional GNN to produce just the QKV vectors, and some other works use 2-branch FFN before network to produce node representation and edge representation separately. Unlike Graphformer is like use a learned edge embedding to like add it into the attention module and then generate a new node representation. And the third point is that they some of the previous attempt adding the adjacency matrix and the inner atomic distance is just that, for this one is for molecular data sets, and for added to this matrix to the attention probabilities. So there's still a learned attention probability, but they are adding the adjacency matrix and the inter-atomic distance into it. And the fourth one is they only aggregate the information from neighborhood. So which means that just one hop, not the one that you can collect along the shortest path. And the last one is they use Ablation eigenvector, which is the same one as Ablation positional encoding. Oh yeah, I wrote it here. So yeah, but this one in the Ablation test, they actually proved that the spatial encoding this work, it outperformed the ones using Ablation positional encoding. Oh, sorry. And for path and distance in GNN, for attention-based aggregation, some of them use to concatenate all the features to calculate the attentional probabilities. So that's just for the aggregation. So different kind of aggregation. So it's just inside the general GNN workflow. And for path-based attention model, they try to model the inference between the center node and its higher order neighbors. So it's still neighbors, but they are only like focusing on the higher order neighbors. And for distance weighted aggregation, they adopt distance encodings as extra node attribute. So yeah, this is just all different kind of aggregations and what they trying to do to like improve their performances. And for different kind of positional encoding, there are absolute Weisweiler lemon positional encoding to represent different nodes labeled by WL algorithm, and also the Ablation positional encoding. So use Ablation eigenvector as the positional encoding. So which is under the premises that nearby node have similar positional features and farther nodes have dissimilar positional features. And for edge features and for attention-based GNN, the edge is weighted by the similarity of the features of each of its two nodes, like how the node representation is similar to the other connected by this edge. So it will be weighted by that similarity value. And the other attempt is to project edge features to an embedding vector, then multiply it by attention coefficient and send the result to an additional feed-forward sublayer to produce edge representations. Okay, so unlike GraphFormer, this just project the edge features to an embedding vector, where the GraphFormer is like trying to learn a more proper and suitable edge embedding by using it in the bias term. So, any questions by now? Okay, if not, I will just make the conclusion of this paper. So first of all, the contribution is that this is a direct application of transformer to graph representation learning. And they add 3 different novel graph structural encodings, and the performance of this model achieves better performances than popular GNNs on benchmark data sets. But there's still some limitation because transformer is such a big model. So the quadratic time complexity of the self-attention module restrict the GraphFormer's application on large graphs. Sorry, I think I call it time complexity, but actually the memory is one of the problems. And yeah, so and as you can see, they are all performed in on those molecular data set, which per graph is not that big. So future works include more efficient runtime improvement, and also add domain knowledge encodings, or different choices of, of centrality encodings, because actually they are using the degree centrality right now. But for some of the case, probably other centrality, like I mentioned, eigenvector or betweenness, or some others like PageRank or cause will probably be more suitable. So adding domain knowledge is probably one of the direction as well. And also the node representation extraction with an applicable graph sampling strategy. And yeah, because this work it's also based on the node features. So node representation extraction is definitely one of its implied application. So with a applicable graph sampling strategy, it could be used on these tasks. Okay, so that's my presentation. And the reference used, this is the reference that the material I used in all of the slides in total. Yeah, so yeah, that is all I have for today. Thank you very much. So if there's any questions.
Okay, so the talk is very good. Any question from students?
There's a question in the chat.
Yeah, okay. So the question is, do you think GraphFormer's performance is partly because of the huge number of parameters compared to other GNNs? I think it's definitely part of the reason, but as you can see, they also compare with other previous attempts of graph transformers, but their performance actually does not exceed the traditional GNNs. So probably that won't be the only case. The structural encodings probably help a lot as well. Does that answer your question? Okay, thank you.
Yeah, any more questions?
I'm curious whether you think the performance improvement for the graph former is related to the fact that all the data sets are chemistry data sets, like maybe the biases that come from the centrality or other encodings do especially well on chemistry problems.
Mm-hmm.
Do you think that that could be the case?
I think that definitely could be a case because for chemistry data sets, it actually it kind of probably more rely on the probably the symmetric feature of the molecule itself. Okay. So probably adding all these structural encodings helped in this chemistry data set, but because the inherent problem of the transformer model, because it's too big, and there's no other sign that they will also perform better in other kinds of data sets. So I think that definitely could be a case that it only works for a chemistry data set.
Oh, thank you.
Yeah, so for this question, I think it's a very good point. I mean, conventionally for graph neural nets, we don't use as much about the chemistry data sets. Normally we use the data set is called Cora, PubMed, and Singer as the data set for testing the graph neural nets. And we also have some larger version of graph data sets for testing graph neural nets. And because I also write some paper on graph neural nets, if you see the paper, the reference 61, actually it's the graph bird, is my paper. The bad news is that they didn't compare with my paper at all, so in the experiments. So I think it's a very good point. I mean, it's not very common to use chemistry data sets for graph neural nets testing in experiments. I think they use a new data set to compare with their new model. And that's probably one of the reasons why they propose centrality as one of the position embedding in the method. So, and they cannot achieve better performance than the other methods. Yeah, it's a good point. Yeah, any more questions from students? Also to the question in the chat, I mean, so the performance difference, I mean, part of the reason is because of the parameter number difference, right? And this question is very similar to the comparison between transform of VIT versus CN. And you see the VIT achieve better performance than CN. Also here, the graph former or graph transformer achieves better performance than GCN models. Also, one of the reasons is because they work in different mechanisms, right? The working mechanisms are very different. For the CN or the GCN model, they still works on the aggregation part, right? So the CN, they use the aggregation via the linear summation, right? I mean, versus the kernel with the templates, I mean, of the images. And for GCN, they also use aggregation, I mean, of the nearby by the edges, nearby neighbors by edges, right? For transformer, they use the self-attention. So I think self-attention contributes more to the model performance than just the parameter numbers, right? They work in different ways. So the self-attention right now is very useful. Normally used in almost every way. So in vision, in natural language processing, also in graph learning right now. So I think this is one of the reasons why it achieves better performance than the other methods. It's not just the scale, the size of the model size of parameters, right? Anyway, it's just a follow-up comment for the question we see in the chats. Yeah. Okay, so any more questions from students? If no other question, then probably that's for today's talk. The talk is very good. Thanks so much, Xiaoying, for the talk. And the presentation is very good. It covers almost everything for this paper already. Thanks so much.
Thank you.
Yeah, so probably that's it for today. And if you have any question for the project, for other parts, you can also attend the office hours, right after class. And also a reminder, it's time for you to start work on your project right now. And we only have about like a few weeks left, before the deadline. So I hope you can start early, then you don't need to rush at the end. And you can also, have some time to polish the papers, right? And for some of the project proposals, I see the proposals are very good. And you may also consider to to consider to make this paper more formal, and you can also consider to publish them in some conferences, about deep learning as well, right? I think it's a good opportunity for you to try to publish some serious research papers at conferences, by taking this course, right? Yeah. So if you have any question about the paper, about projects, or some other questions, you want to attend office hours right after class, and we can have a deeper discussions. Thank you so much for your time and attention, and probably that's it for today's class. Thanks. Oh, let's also thank the speaker. Thank you.